This talk is instruction reordering. It's happening all the time, at compile time, at run time. This is life. This is how the world works, mostly because of latencies. So the talk is really going to be underpinning the C++ language. We have this as-if rule. We author code describing the intent of the algorithm. The intent is respected through dependencies. Stuff moves around, that's not a problem because the intent is respected through dependencies. That's how we reason about well-defined behavior. So that's today. There are two talks. We're only doing one of them today. It is CppCon, right? There's so many good talks, they didn't have a double session available. We're doing the more practical end, which is sequential versus logical, data flows, control flows. We're going to talk about that. That's actually how we're going to reason about our code. There's another talk that we could do that discusses the phenomenon. Why is stuff moving dynamically in weird ways at runtime due to internal things going on inside the CPU, the cache line, other stuff in the system? And that's kind of interesting if we want to reason about errors. But the phenomenon is secondary. As it turns out, there is a talk where we talk about the phenomenon inside the compiler, inside the CPU. At C++ Now, there's a YouTube video, here's the link, and that goes into, in this case, went into GCC, and then inside the CPU to talk about the phenomenon and how and why it occurs. But today we're going to stay with the physical and logical sequence, and here are the goals. We do care about dependencies, that's how we author algorithms. We do care about data flows and control flows, that's how we reason about what we wrote and how it's executing. That'll be respected. Be respected by anybody who looks at the code, the compiler, the CPU, they'll all respect that. Reordering is going to happen, that's life. That's latencies. You go talk about the phenomenon for why that occurs. C++, we're so close to the hardware, we reason about it directly. The language gives us tools for this. But for the most part, we have to be, as authors of code, as authors of algorithms, we have to be flexible about, I say, this is my intent, this is my algorithm, these are my dependencies, these are the mutations that occur over time, side effects will maybe happen. This is my algorithm, and we have well-defined behavior. We can do that, but everything we write is going to move at runtime. And after today's talk, that hopefully should be obvious. And this is really kind of the question. What is sequence, top to bottom, left to right, is kind of what we might assume. And what's its role? So the agenda. We'll talk about sequence, what it is. We'll talk about assumptions in design. Assumptions, you can't help but make them. We make assumptions all the time. The world is big and scary. We have to make assumptions somewhere. Imperative versus sequential devices. We'll talk about that real quick. Physical versus logical sequences. Physical is a nothing. You won't even be able to reason about it. You actually can't even define it. We'll talk a little about that. And sequentially, you can deal with that. That's higher order dependencies and abstractions. The as-if rule, we'll summarize with that. And the phenomenon, that's another talk or another day. Okay, so this is the summary for today. So this is the takeaway. You can kind of fall asleep after this slide. You can't control instruction order. You can't, sorry. You can control dependencies. That's good. Everybody agrees. The compiler agrees, the CPU agrees, the C++ language standard, we all agree on well-defined behavior. That's what we worry about. Dependencies are how that occurs. So you might think you care about instruction order, you don't. It's going to move for no reason whatsoever. It's just crazy and nutty. It'll make you crazy if you try to go there. Don't. So for the most part, if you can be a little bit more flexible in your thinking, focus on your algorithm and your dependencies, focus on well-defined behavior, nothing is surprising. Just assume lots of stuff moves, but your dependencies are always respected. And so, I kind of want to pick, real quick before we leave that, there are a dozen ways to say this, and that's the rest of the talk. I have a dozen ways to say this slide. Dependencies is all you worry about. So our job today really is, I want to paint a picture for this dependencies good, physical instruction order, it's a nothing. You can't do that. It won't be controllable. It'll make you crazy. So we have a dozen ways to say this, and that's the whole talk. That's all we're doing, a dozen ways to say this. Okay, so your code did execute, and it executed correctly. You may not have gotten the value you wanted, but you got the correct value because of your dependencies. So you should be confident in your compiler, trusting your CPU, grateful that instruction order you mostly don't need to worry about. Physical sequence you don't worry about. That's not something we worry about. We do worry about dependencies, algorithms, well-defined behavior. That's how we author code, construct, scale our systems. And as long as your tools stay there, you're good. So the moral of the story, it's our job to implement for dependencies, that's everything. And it's crazy to just focus on physical instruction sequence because you're not even going to be able to get away with it. So for the most part, you shouldn't have to know this stuff. You should be lazy to say, here's what I want, I authored code, we have intent, it's there through well-defined behavior. The compiler will mess with it, the CPU will mess with it. Don't care, my intent is clear, everything executed, the intent was respected, I got the correct value and also the value I wanted. That's the goal. So a moment on this definition of terms, assumption. An assumption is any perceived truth. It's not true, it's perceived to be true. Any perceived truth that is uncontrolled in the design of the implementation. So if you author code, int a equals 1, int b equals 2, and you assume those happen in that order, that's an assumption you might make, but that's not true. That's not what the language says, it's not what the CPU and the compiler are going to do. So it's easy to make assumptions. We fall into this trap a lot, but you got to kind of watch them, and you can watch them by just staying with dependencies. So that's today. So there is no guarantee that your code will execute, your statement will execute in the order you specify. Instructions will reorder. It actually happens for a lot of reasons for all languages because everybody runs on a CPU. Everybody kind of goes through a compiler at some level. We're pipelining. That's why this is happening. There's no guarantee, but that's not a problem because the dependencies are always respected, the logical sequence is always there. So you want to be like Buzz Lightyear on the right. This is so cool. If I did not have my code moving around at runtime, everything would be incredibly slow. That's the other talk, the phenomenon. So don't be like Woody, who's shocked that the code moves. The code's going to move. That's life. It will move. So don't freak out. It's not a big deal. This is a great thing that the code moves. We have that in C and C++. It's not chaos. There are rules. And if anybody wants to jump in at any time, feel free, pipe up. We have well-defined behavior. We can reason about stuff. What are the rules? Well, I'll just tell you the rules. We have well-defined behavior in the language. The compiler, it worked. CPU, it ran correctly. The laws of physics. And that actually is the big one. Latencies occur. It's on the chip, it's off the chip, go across the data bus, gets paged to disk. I'm fiddling with stuff that's not here right now. And the latencies will propagate in, stuff is going to stall, bubbles get inserted into the pipeline, and ideally we would still like to make progress on something while we're waiting for something that doesn't exist here on the chip yet. So these are all the rules. Now if you're at a really, really big scale, stuff breaks, that's true. But for the most part, these are the things you can rely upon, that you can reason about, and anything that's not this might be an assumption you make, and we make assumptions all the time that are not on this list. Those are errors in the system. Those are failure scenarios. Okay, sequence. It exists. We use it to reason about procedural algorithms. So here's kind of some ABCD. It's a tool. That's cool. It's how we're trained. We follow our training. It's easy to understand, one letter at a time, beginning to end, statements top to bottom. And we do think it adds value because it does, especially with things that we're unfamiliar with. We can start tracing out, well, what's this do? I don't know, and you trace it out, and there's a sequence there. We're trying to figure out what's going on, and that's how we're going to inspect into the system. So just kind of this, we got a lot of content, so I'm just going to kind of blow through some of this, but sequence is how things are going to mutate over time. And that's not a big deal. That's our system. That's what we want. We want changes over time, side effects, stuff. We got to manage that somehow. But you got to have some guarantees. And this is our logic, the basis of our algorithm. It is how we're trained. We have sequence, selection, iteration. These are our building blocks for all algorithmic languages, right? That's how we put together higher order logical reasoning. So, that's there. And it can be easier to understand. I'm here, I don't know what this code base does, and I trace it through, and in time, I kind of figure out how it works, how it flows. So we start to make assumptions based on, well, I'm assuming that call occurred, but that call may not have completed. If it started an asynchronous thing, if other things are happening in parallel, you in your head might assume sequential order of completion, but the code may or may not respect that. You have to look at the APIs to design the problem. It's kind of our go-to tool. When in doubt, the world is big and scary, sequence is something we can understand. I have no idea what that system does. You hop in, you follow a sequence, and you figure it out. So we do care. This is good, but there are other ways to think. So we have declarative programming paradigms out there. They don't deal with sequence at all, declarative programming. They don't do sequence at all, conceptually. And some languages, like C++, do not grant sequence this level of reverence. C++ says we have the as-if rule. Stuff can move around. Your dependencies will be respected. You'll get well-defined behavior, but stuff's going to move. So don't assume sequence in C++, because that's not one of the guarantees. How does sequence relate to algorithm? Well, an algorithm is not defined by the sequence of statements. It's not. An algorithm is defined by the sequence of dependencies. So sequence, it's a tool that we use to manage dependencies, and from the dependencies we build up an algorithm. What defines an algorithm? Well, we kind of already know this to be true. So you wrote your code and you compiled it with optimization or not, or inline or not, or for different architectures or not. It's the same program. Well, how could it be the same program? The binary is different. The dependencies were the same. It's the same program. Oh, okay, well, after I load the program, I'm going to do the address load randomization, and I'm going to hook up to libraries or shared libraries or DLLs that weren't there before. So it's the same program. Well, how could it be the same program? You've got a different binary. It's because the dependencies are the same. And a self-mutating virus, I wrote this code, it's self-modifying code, and it's doing something and infecting and running around. It's the same program after the modification. Well, how can it be the same program? Well, because the dependencies are the same. The dependencies are the same, therefore it's the same program. So we already know this kind of to be true. So logical dependencies are actually what's important. The physical sequence, it's a nothing. It really is not relevant. So let's talk real quick, lines of code. We add lines of code, we remove lines of code, we move them around, we reformat them, we manage them, we build and ship them. But that's not our job, that's just what we do. It's how we keep the workshop clean. So our job, we're professional engineers, we need to analyze and understand, design and implement our algorithms and stuff, all based on this logical dependency thing, mutation, side effects, whatever. We have to manage that. It's hard, it's complicated, that's why we're professionals when we're dealing with it. But lines of code is not the thing. They're gonna move, we can move them around, but also the compiler will move them and the CPU will move them at runtime. So just real quick, from little to big, at the small scale, we kind of know this to be true. So we reason about dependencies and order of operations and that kind of stuff. At the big scale, we start talking about coupling and transactions and status and phases and stuff. But it's really all just dependencies. That's all we got going on. We got state, we got mutation of state, and time slices and zones of life and versions of things. Managing that is kind of our job. Little to big, it's all a problem of dependencies, not physical sequence. So here's Turing trains. This is kind of fun. You can find these on the web. People build them out of Legos. So it's just a little track here, and you have a little train that runs around. So you can see like the count and clear function. You can, as the train runs, the little gates flip, and you build these things. These are kits. So you can do all kinds of logic circuitry here. But the goal here is that there is a sequence, but it's the logical sequence. This gate is flipping before that gate. And in the end, you can look at a snapshot of state over time, but understanding the system is understanding the dependencies, which in this case do mutate in order in some reasonable way that you could trace. So here's something a little different. Recurrent neural network, haven't seen it before, no problem. We can, we're software guys, we can figure this out. So we got state machines, and we got all these nodes here. Looks like some nodes come down. Nodes come out. Okay, well, the down probably comes before the stuff coming out, but it's not the physical order of when stuff happens. We have lines connecting nodes to nodes, and we can kind of figure out the state changes and what it impacts from other things. So it's the logical dependencies mutated through a sequential execution that's actually important. The state and the nodes and the snapshots of states over time, the logical dependencies, they're important. The physical sequence, it's actually a nothing. That was why we care. Why do we not care about sequence? And a big one of the biggest ones is constraints, unnecessary constraints. They propagate into our system largely through assumptions. Constraints are good. We want them. Now we want good constraints, not bad constraints. So you sit down, look at a blank screen, infinite flexibility doesn't do anything. We start adding constraints and rails to the system, and eventually it starts giving us behavior we want. We've created a system. So we want necessary constraints. We don't want unnecessary constraints. And if you have a missing constraint, that means there's a dependency that was important. You didn't track that, and that'll be violated eventually, and you'll have a system failure. So constraining for sequence. Constrain what's necessary. Don't constrain what's necessary. And if you don't care, do not specify. That would be the goal. That'll open up the door for parallel and other stuff. So dependencies are how we go. There's no such thing as a neutral constraint. You're always specifying a restriction, and we want restrictions so the system exhibits rational, well-defined behavior bounded by what ultimately we want the system to do. Necessary control. It's necessary for us to say what we want, but we don't want to say what we don't want. So exerting necessary is actually our design and implementation process. We live here. This is what we do. And it is very seductive and easy to start saying, well, I'm specifying stuff left and right. And then you start specifying stuff that you shouldn't have specified. You should have been silent on that. And that's going to start restricting behaviors and options down the road. But you do want to specify expectations, and you do want to be able to make valid assumptions. That's based on saying, look, this is the way this works. I put a stake in the ground. I can make assumptions based on that. And you start scaling your system from that. So unnecessary control. All assumptions are eventually violated. They restrict your options. Now, restricting your options is good because now I can make assumptions based on what I know to be true. But if it restricts my options based on something I don't want to be restricted on, then that was a bad restriction. So this is a tough line because if you exert too much control, you choke the compiler and you choke the CPU and you disallow efficiencies. And you also disallow your feature set and your system to behave in the way you wanted. But you need to specify some things, otherwise you don't have a system that actually behaves in a reasonable way, something you can reason about, or something that does ideally what the system's supposed to do. Okay, so instruction order for the most part, penalties a lot if you add unnecessary restrictions. Efficiency, correctness, effort, a lot of penalties when you start adding restrictions you don't need. We want to add restrictions so that we can reason about our systems. But if you add too many, a lot of bad things happen. So, I'm just going to kind of move through this. But avoid when possible. You shouldn't care about a lot of things. Mostly you shouldn't care about physical sequence. We design and implement based on dependencies. So kind of jumping through. Order assumptions in design. You can't help but make assumptions. We're about to go through a scenario where we're going to make assumptions. I'm not going to make any assumptions when I go. You're going to make assumptions. It's the way it is. You fly, I buy, so that's the little colloquialism. I will pay for the pizza, you go get the pizza. So, you fly, I buy. How many assumptions will we make? And, try not to make an assumption. Good luck with that. So here's our algorithm, our design, our control flow, our user story, whatever we want to call that. So I'm going to say, here's what I want, this is the pizza I want. I'll give you the money, you go to the pizzeria, you order it, they make it, you bring it back here to me, I have it, I eat it. What is the necessary order? These questions are kind of like universally interesting questions. What is the necessary order that this would occur? For which should we not care about order? Anyone want to take a shot from our algorithm? For what do you not care? Yeah, I don't care about when you get the money. Maybe I can get by without paying. That'd be great too. Actually, we care about 10. We don't care about anything else. I want to be eating pizza. Screw everything else. I don't care. Don't make me care. I don't want to care. I can't eat it before I have it. So there is some kind of a dependency here to where I better have it so I can eat it. So you're going to start to see dependencies build up. But, this is kind of like a breakdown, and we'll just kind of walk through very, very quickly because, you don't need to beat it to death. But I can tell you what I want in the phone while you're driving, so I can move that around. Money's the big fiction. I can pay before or after, prepaid coupons, whatever. You can drive, and I can tell you, these things can move. They don't really matter where they occur. And these questions, there's only two things I'm worried about when we get close to the bottom here. I have it. Oh, we're starting to get really constricted here as we get close to the end of the algorithm. And then I have there were only two things we cared about. I'm concerned that you might bring me the wrong thing. That would be bad. I'm concerned that transaction success might be jeopardized, like I didn't pay for it or that we didn't get the pizza or something like that. In this algorithm, those are the only two things I actually really cared about. All the order stuff I didn't care about really at all. We could start specifying order, but they're kind of like irrelevant. So the pipeline is going to say those things might actually move at runtime, and that's going to happen with our code. So what did we consider? Well, we did talk about the algorithm. I want to be eating pizza. That's a good thing. And we talked about a sequence of steps. We laid out a control flow. We defined state and dependencies and some mutation of state. My wallet got lighter somewhere through that transaction. And this is the active programming, but the active execution is that other thing where we actually don't care about a lot of those details. So there are alternative algorithms. That was one. Where'd it go? I'll just zip to it. My PowerPoint skills are minimal. Sorry. Okay, pizza, yay, they jump around, oh look, dynamic, whatever. Okay, preferences. We did talk about, what we want, but there's a lot of bias. Do I want to pay for expensive pizza, good pizza, what? Constraints, like the limitations of the target architecture, that's going to bound our algorithm. Preferences are going to reorder our instructions based on what we want to optimize for. Constraints will limit our algorithm based on what's even allowed or how we may even be able to express an algorithm or options to the algorithm. Over specifications, these are things that, I didn't want to specify this constraint, but I did. I just kind of fell into a lazy assumption about stuff, and I started specifying stuff that was not relevant. It bounded, it restricted, it limited the options that the compiler and the CPU were able to express when they executed. So, it seems like all of these may influence instruction order, and they do. They all do. So, preferences, hot, good, fast, cheap, what kind of pizza do you want? Some pizza places are farther from your house. Maybe you want to go to the one run by your cousin Vinny. These are going to influence your instruction order and the execution of your instruction order. Constraints, this is Howard and Sheldon on Vespa, the Cadillac of scooters, or there's a phrase there I can't remember, but whatever. If you don't have a vehicle available, then you're going to have to come up with alternative options or get something closer that you can walk to or bike to. Money, when, day of time, some places you can't go eat because they don't have what you want. So these will influence your instruction order. This over-specification, this happens all the time, and it's so seductive, it just slips in. I want to pay, but I don't want to leave the house. I care about 10. I don't care about all that other stuff. Now, you might want to add preferences and constraints and stuff to say, well, I only want a good pizza. You might add additional restrictions, but for the most part, you can redefine the scenario quite often to come up with an alternative algorithm that will still get you pizza, but you didn't actually go through that other algorithmic ritual. So over-specifications are usually done by revisiting for what is it that's important, me eating pizza, what's not important, everything else, or no, I'm going to rank what else is important. I want something good, I want something hot, whatever it is. So this is kind of the second half. Over-specifications, they limit options, they confuse and hide stuff, they slow our systems, they break our systems. Over-specifications break our systems because we restrict what we want to express and we don't hit requirements, or we add assumptions that were unimportant and then the assumptions get violated. So real constraints, sometimes you'll want to relax those. Erroneous constraints have negative value. So here we go. Requirements influence instruction order. Preferences influence instruction order. Constraints influence instruction order. Number 4 we didn't talk about. This is that whole other talk. There is a translation activity that occurs. You type C++, but the CPU is not running C++. You went through some kind of compile and link process, and it loads up and it runs. Well, there's going to be a lot of communication friction as you translate from one language, C++, to another language, something, 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 and then ultimately assembler or object code or something. And there's going to be a revisiting of concepts and dependencies all through that process. The dependencies will be respected, but the physical instruction sequence will not. It cannot. So number 4 is actually the other talk. Reality is saying that we got to go through the compiler and the CPU, and then the CPU has its own scheduler. So, good luck predicting that. So a lot of these are compile time, runtime stuff, but for most part, requirements, software development tends to do these, compiler optimizations, this kind of be a build time, it can be a load time thing. Constraints, we have restrictions based on the target architecture, CPUs, memory footprint, something. And translation, of course, you've got a multi-stage process to kind of get agreement across all of the tools as they iterate through, respecting your algorithm, respecting your dependencies, respecting your well-defined behavior to something that actually executes in a very weird way very, very far removed from the code you actually wrote. Okay, imperative versus sequential devices. So this can be really interesting to contrast. We have a lot of options, especially in C++, on how do we want to view control structures, how do we want to view languages, how do we want to author our system. So imperative is do this, do this, do this, do this. That's imperative. Well, we have a lot of programming paradigms. Imperative is do this. So like if you're writing an RTOS, a real-time operating system, you want very exacting control, you're going to pay for it. But you can get very exacting control with imperative programming. Well, this is just adapted off of Wikipedia. Imperative, structured, procedural, functional, different ways to program. But these are starting to build on higher order control structures, an alternative view to expressing dependencies. That's really all they're doing. And then, of course, it's going to execute on some chip somewhere. So imperative devices are controlled through imperative programming. You're going to do this, do this, do this. I'm taking control. I'm going to pay for it, but I can take control if I want. That's imperative. Sequential devices are controlled through structured and procedural programming where instruction dependencies are critical. So we'll look at some of the higher order control structures. But imperative is do this. And now we do have this elemental table where we can talk about the individual atomic structures. And those are helpful to reason about things like, oh, I want to do a lock-free algorithm or something. I need to be able to reason atomically about what's going on. So, it's okay to reason about the elemental table. That's useful. The elemental table does not exist in the real world. In the real world, we have molecules and compounds, and most of those elements don't run around as a single atom. They run around as pairs or ions or whatever. So the world is control structures. The world is molecules, but it is helpful to reason about the atomic table. It's helpful to reason about the atomic control flows. So atoms are interesting to understand and reason, but only at the atomic level. The vast majority of time we live in the real world, which is higher order compounds and structures, dependencies, electron chemistry. Sequence of what? This is kind of an interesting problem because software engineering, you think it's a direct activity, but it's not. I wrote this code and I said, do it, and they did it, and something popped up on the screen. I controlled that. You indirectly controlled that. This is an indirect activity. We author a framework, a structure, a road with rails, and somehow at runtime, the cars are going to zip through there. So what we do is architect indirectly a framework that we trust the compiler to respect, the CPU to respect, and at runtime, they will respect that. But everything we did is like buffer lanes on the bowling alley to hope and pray everybody respects the lane we gave them. So this is a sequence of dependencies. We're talking about data flow and logical control flow along the roads. We build the roads, we specify the roads, but it runs on the roads, whatever it is we specified. And the implementation is the next slide. We design our framework to influence the execution, but we don't do the execution. I'm not the CPU. I can't go that fast. I design my system to influence what the CPU does. So everything we do is indirect. So I will provide the program structure and the control flow that I want respected, and the compiler will respect that well-defined behavior, so will the CPU. But at runtime, hands off, I'm going to trust that they do their thing because we aren't that fast. We're not actually executing those sequences. So the car is the data flow and the instruction sequence, and this indirect activity is kind of helpful because it allows us to say, I want to say these dependencies are my system, and as long as I'm clear about that intent, the as-if rule in C++ says everybody all the way through will respect that. So we're going to pick up the speed a little bit. This is sequence selection iteration. These are kind of our building blocks for algorithmic programming, if you're into that kind of thing. And these are the mechanisms we're using to establish sequence, but it's a sequence not of instructions, it's a sequence of dependencies. Imperative, you can do imperative, do this, do this, do this, do this. You're going to pay for it usually. It's a lot easier to establish a framework and have somebody else budget a lot of the details that we don't want to budget. But superscalar CPUs, for the most part, you're not doing imperative. You are doing some higher order dependency specification that some other device is going to execute with your specification. So superscalar CPUs, the instructions are going to jump over each other. That's the other talk. So a review on sequential. We can reason about behavior, mutations, and Turing complete. We can reason about a lot of things at a higher order sequential because we're reasoning at the level of dependencies, not reasoning at the level of physical instruction sequence. So this is kind of interesting because the contrast is so good. An imperative device would be like the minion there. That's Dave. And imperative says, you're in control. Do this, do this, do this, do this. And the whole point of do this, do this, do this, don't respect dependency. I say jump off a cliff, you jump off a cliff. I say run over here, and you run over there. That's the whole point of imperative. You want to disregard dependencies. And there are scenarios to do that. Where that's a desirable element. Like in RTOS, that would be a desirable element. But because it's oblivious to logical dependencies, these things are hard to scale. It's hard to scale because the complexities creep in, the dependencies get violated, because the value of it is that it does not respect dependencies. So you can't scale imperative, but on the sequential, it's goal-based logical procedures, higher order logical structures. This is what we actually scale with. So we want to work with dependencies. So here's working with imperative devices. You can do this, limited hardware and RTOS kind of thing. You will queue all future tasks. You will perform all scheduling. You will identify all dependencies. You will manage all dependencies. You'll identify opportunities for efficiency. You'll respond to unexpected events because they're going to happen. You're going to concurrently interface with external subsystems, and you're going to continually establish further constraints as, how did this happen? Well, you found a constraint that you should have bounded, and you're going to continually improve and repair your system because this is chaos, because dependencies are not respected. That's the whole point of imperative. Sequential is so easy. All you have to do is establish an algorithm based on logical dependencies, how all algorithms are established. Establish objectives and priorities. Establish constraints, how it interfaces with external systems. You're done. These things scale. So this is a lot easier, self-organizing, whatever. You can throw exceptions, reassembles, and it's good. Imperative is simple. Sequential, it's simple in a different way because your dependencies get respected. But for the most part, working with imperative at scale is chaos. It can't be done. Working at scale with sequential is very manageable as long as you stay with dependencies. Your CPU is actually a sequential device. It is not an imperative device. Now, there's some very limited CPUs or old CPUs that are more imperative, but for the most part, the CPU will trace internal and external dependencies at state in the cache line and propagation across the data bus into main memory and out other places. The CPU is going to trace all that stuff, and it'll parallelize execution prefetch data, speculatively execute instructions while managing cache coherency across all those levels and managing internal metrics to decide what it can run and how it should reschedule stuff on the fly to constantly optimize on the fly how your algorithm executes. So you're not going to be able to second guess this. I mean, you can severely hamstrung your CPU if you want, but for the most part, that's generally not a good thing. Well, it's inefficient. Physical versus logical, what actually happened? Okay, there are two kinds of sequence, two. Physical sequence is defined by the order in which your instructions occur. Funny word, occur. The order you specify them in your source file, the order you serialize into object code after that huge sausage-making festival with the compiler occurs, the order they're presented through the program counter, because the CPU is actually executing instructions that never go through the program counter, that are started in the CPU, that are completed in the CPU. Instructions take different lengths of time in the CPU, and a single core is running a dozen of them at the same time. That the results are propagated back to main memory or the cache line. So when did it occur? This is not meaningful. You can't even have a discussion about when it occurred. Pick a metric, but your metric is going to be not very useful. Now, this side is very easy. Sequential, it's defined by logical dependencies. Well, that's based on well-defined behavior. We know what that is. This is easy. So, again, we're back to, slide 1 saying this is the talk today. Another way to say, here we go. Int A and B. A is 1, B is 2. What can you say about A is 1 and B is 2? 1 is assigned to A because of right to left associativity. 2 is assigned to B because of right to left associativity. What can you say about A and B? And, well, it says right there, nothing. And the reason it's nothing is, well, after those lines execute, I know A will be 1. That's well defined. A will be 1, B will be 2. I don't know when that happened. I don't even know if one happened before the other. They may move, but I know A will be 1 and B will be 2. I know that to be true. I can reason about that. I just don't know when. Don't assume when, because that will bite you on the butt. Best algorithmic tools. There are 3 that are so obvious. I didn't even have these slides when I did this talk before because they're so obvious I didn't even think about them. But in essence, we have logical dependencies that we establish across statements. And we'll see a slide on each of those 3 in a second. We have operator precedence and operator associativity. We know what those are. We see them. We know multiplication happens before addition. We know that. But, that's really, really powerful, especially the functional kids will talk about that. So when you get mad, you can go ahead and throw in your mutex or your atomics or your lock or whatever. But logical dependencies. Identify the state you're using, resolve it, use it, and then you're good. So here we go, int A and B. A has a value. On that first line, what is the value of A? It has a value. It's an int. It has a value, but we don't know. It's some garbage value, right? Maybe it's a 12, maybe it's a 0, who knows? A has a value. Oh, look, we assigned 1 onto A. We did violence to A. A has been mutated. It has a new value. Oh, and now I see A is being used. And in the line after that, we mutate A again. A has 3 different values on this slide. Which value of A should I be using? Well, that's well defined. We're going to use A is assigned the value of 1. 1 is assigned to A. We know what the value of B is because we know what the value of A. We can reason about this. You don't know what order those statements occur, but you do know some things. You know the compiler will give B the value, the known value, based on A being 1. That's just the way it's going to be always. That'll never be violated. So when all this stuff moves around, most of the time we don't know because everything is obviously good. So static single assignment, that's inside the compiler. That's basically talking about how this works. Associativity. We know what the value of B is. So B is given the value 1, A is garbage value. We have a pointer to do indirection on the A value. We're going to hammer on the value of A indirectly through the pointer P by pre-incrementing the value of B that it came from. We know what the value of A is. At the end of this, A is 2. Why? Because we have language rules and well-defined behavior based on operator associativity to say when things are computed. These statements may move around, they will move around, but A will always be 2. We can reason about that because we know operator associativity is preserved. The compiler respects it, the CPU respects it, it's defined in the language standard. Operator precedence. We know the value of B is 5. We know. Stuff can move around all at once, but B had better be 5. And if B is not 5, your compiler's broken or your CPU's dead or something. So precedence associativity, these are very, very powerful tools, and this is actually the underscore of the entire functional programming world. So physical sequence, so here's a function, highlight row and column, mouse comes in, and based on where that mouse landed, compute the row and the column, and I want to turn a color on the column, a color on the row. This is what this function does. Okay. And we assume it's going to execute top to bottom, but it's not. But in this case, we're going to compute the row and column index. We're going to do is the row locked? We'll have a different color if the row or the column is locked. And we get the color for the row, color for the column. We highlight the row, we're done. Okay, that's great function. And order, we can reason that this executes top to bottom, but it won't. Stuff will move around. The dependencies will be respected, but when we talk about the syntax and the semantics and the well-defined behavior says all those statements are allowed to move, but the dependencies will be respected. So all the programming languages have this in common, but C++ is a lot more clear about what is well-defined and that we specify through intent of dependencies in our algorithm. And that's why we're giving explicit license for the compiler to mess with and the CPU to mess with the reordering of all our executing sequence. So I'm going to jump through, but just real quick, undefined is a lack of constraints and unspecified is a constraint violation. And, everything's going to run on a CPU that we don't directly control. Okay, so this is that same function, and all I've done is I said, well, let's do all the row stuff, and let's do all the column stuff. And this function still works. Now, I, as the author of this function, I could have moved those statements around, and the function still works. Works just like it did before. Well, if I could have moved those as the program or the algorithm author, the CPU could have moved them. The compiler could have moved them, and they will. And this is the same function behaving correctly in a well-defined way because these sequential dependencies are still respected. So just kind of looking at how to trace control flow, data flow. Here's another example. How do we find the dependencies here? Well, anytime you use state, you have a dependency. It's just the way it is. So you kind of want to use state with care. Because when you use state, it must be fully resolved before things subsequent can rely upon it. And those are going to be the dependencies. that we use to express algorithms that are respected through the well-defined behavior of the language. And the compiler will respect it, and the CPU will respect it. So beware of overriding and mutation because there's a little bit more work. But here, essentially what I'm doing is I'm highlighting all the assignment operations, and 1 is assigned to A. Well, 1 is a constant, so that state's kind of like resolved already. So, that happens. But every time I'm doing this assignment state overriding thing, there's going to be stop, what is the state I should overwrite, find it, resolve it, smack it on that value in memory. So assignment operators, this is why functional languages don't even have the assignment operator, because they don't want to deal with this. So there are languages that don't have the assignment operator because you have to resolve state there. So state, it can be tricky sometimes. You'd like to think it wouldn't, but this value that you're using, it might be the correct value, but if it's not the correct value, which value is it? Oh, well, that version was too old. Oh, that version, it's corrupted because it's like half an update and you can't use it yet, I'm busy. Or it's too new. You used the wrong value because you should be using that other one. Now, cache coherency, the CPU will kind of manage all that internally, but in the algorithms we define, if we don't specify these dependencies, then this is where we're going to get bitten a little bit on state. So 2 issues, you got to compute the state and then you got to change the state and you got to resolve through. So you state with care. This is assignments and a change in state. This is going to go a little bit into the functional programming thing. You have dependencies to compute the right-hand side before you can assign it to the left-hand side. So on the assignment operator, we have right-to-left associativity because you got to fully resolve that right-hand side and then smack it on the left. But mutation, it's a lot more work. Functional tries to avoid assignment in general, but mutation says you got to compute the right-hand side, then you got to compute the left-hand side, and then you got to mutate the left-hand side. So that's this next side. But the functional thing says state is evil, everything's computed from first principles. So the big push for functional programming is to handle dependencies because they're complicated, and state mutation is complicated. So the languages that say, oh, it's a functional language, it's just because of this. And so here's the resolving problem. If it's a constant, it's like not changing, you're done. How could you screw up? And if it's computed, well, A and B, as long as I know the value of A and I know the value of B, I can compute the product of that. Well, overriding, well, I'm going to do this right-hand side, and I got to fully resolve that. Then I got to go find that thing on the left-hand side that I can do violence and beat the heck out of him. And while I'm beating on him, nobody else better be messing with him because, I'm taking control of overriding him. Mutating is the most work. Mutating is I need to know the left-hand side value so I can mutate it based on the right-hand side computed value. So in practice, complexity increases nonlinear. You might be tempted to say that's a bad thing, but it's not a bad thing. We want complex systems. It's essential that we solve complex problems. So these are tools by which we get increasingly complex things. And reasoning is actually pretty simple, and this is your spectrum. No data object, how can you go wrong? Const data object is not changing, so you're probably not going to shoot yourself in the foot. You probably can't. It's the same value. Computed, well, as long as I can resolve the values, I can dynamically compute. And that's the functional end of the scale. We're C++, so, we'll overwrite and mutate. But those things are the most work. So your algorithm can hang out on that side if you want, or hang out on this side if you want. Some of the languages force you onto that far side, but we're C++, you pick where you want to go. So here's the same kind of thing. I'm going to zip through. We're going to shuffle. We're just going to shuffle the assignment statements to the bottom. This is from before. But this is the summary. Any order that respects your logical dependencies is logically equivalent. And when you go into the compiler and the CPU, we beat on that to death. Any order, stuff can move all you want as long as the dependencies are respected. That's the whole goal. Okay, so physical sequence, we don't care. It moves around for no reason whatsoever at runtime, at compile time. And if it's not a logical sequence, you shouldn't care. And the statement's interesting because on a physical sequence, no dependencies exist, because if there were dependency, we would have respected it. The compiler would respect it, CPU would respect it. If there are no dependencies, then you cannot enforce order. That's the whole point of being a physical sequence. Okay, so the as-if rule, summarizing up. It's really a great rule. It gives full carte blanche license to the compiler and the CPU to do whatever they want. Our dependencies will be respected. And it's the cool rule. Essentially, you've got this biggest possible breadth of option that you've handed the compiler, a license to the compiler and the CPU to reshuffle that horrid atrocity of legacy algorithm into something that's somewhat sane at execution time. And so the dependencies will be respected. Everything else is not respected. That's the whole point of the as-if rule. Here's the rule. Section 1.9/1, The semantic descriptions in this international standard assign a parameterized, non-deterministic, abstract machine. It's an artifact, it's a machine to explain the standard. This international standard places no requirement on the structure of conforming implementations. The standard, the big fat standard, if you read the thing, it's two things. It is the explanation of observable behavior. It is your well-defined behavior. It is the basis by which you can author, operator precedence, associativity, whatever, to establish algorithms, how to reason about your stuff. It's well-defined. It is also a description of an abstract machine, an artifact to explain how it might work in an implementation, how it might work in a conforming implementation. You can disregard that. It's an artifact, but you can't say, and then magic happens. The standard doesn't say, and then magic happens. It gives you an example of how it might possibly happen, but it's an artifact. Okay, so the as-if rule in practice, that is licensed for the compiler vendors and the CPU vendors to do whatever they want with our code, whatever they want. As long as we assign the right values, precedence, associativity, all that stuff, whatever the well-defined behaviors in the language are, as long as they respect our dependencies, they can do what SIMD, don't SIMD, inline loops, unwrap stuff. They can do whatever they want to make it go faster. And the corollary is you should kind of expect that they're going to do some stuff like that. And they will. They have to. They can't not do that. So comparing with other languages, now we are defined based on this concept of intent. Other languages often are defined in the concepts of a conforming implementation, a behavior. So if you don't behave like this conforming implementation, bugs and all, you're wrong. So, we don't have a conforming implementation. We have intent. We're saying A will have this value after it's assigned this thing. Because our stuff is that, we stay with intent, give license to the compiler and CPU to move stuff around. This is something I grabbed off the C++ standards list early this year. I thought it was a good quote, so I threw it up there. It's not like other languages. We author code, which gets translated into as-if code. The CPU runs as-if code. That's kind of what he's saying. Your whole job is to specify intent. And you got the tools for that. You have well-defined behavior for that. So as long as you stay with well-defined behavior, you have the tools to express whatever you want. It's going to run correctly. You'll get the correct value. So, there we go, expressing intent. We manage intent, we allow for optimizations, and this is kind of interesting, I'm not writing performant code, I don't care. Well, that it's tough to say where that line is, but the short answer is, you want to write code that runs on a CPU, your code will run on a CPU, and you've granted the CPU maximum latitude to optimize. So this is really a unique language feature C and C++ have, which is really highly valuable, but also it says, use your tools. Your tools are logical dependencies, author algorithm through intent. So the takeaway for today, don't think imperatively, there is a chance that your code will execute in the order you typed it in. There is a chance. It's not a good chance, but it may happen. Your dependencies will be respected, but it's going to move. It can't help but move. Logical sequence is defined by dependencies. We have language rules for that. Focus on dependency management. That's kind of our job from little to big. That's how we build all systems. And granting maximum latitude to the tools and the underlying execution to indirectly execute the bounded roads we give it, that's great. So we get the fastest, most efficient programs. We also work at the level at which humans want to work. So dependencies are respected. If no dependencies are present, order's uncontrolled. You're saying I don't want to control order here because I didn't put a dependency on it. If you wanted to put a dependency on it, put a dependency on it. If you don't want it, order's uncontrolled. Everybody agrees on what a dependency is. The compiler agrees, the CPU agrees with the language committee on what a dependency is. We have the tools. They all disagree on what is a statement, what is physical sequence. Who knows? I mean, it doesn't translate through at all. There's a lot of sausage making in that process. And how would anyone think that what you have here on the screen executes on the CPU? It can't possibly happen. So don't make assumptions regarding order. Order doesn't matter. Make assumptions regarding this dependency is resolved, because I put a logical dependency in place that will be resolved. Over specifications, they're bad. Get rid of them when you can. As-if rule, compiler and CPU do whatever they want. Inline or not, return value optimization or not, unroll loops or not. We're giving them a lot of control. And in the end, we actually get more scalable, flexible, efficient, and simpler systems. So this is just kind of a little contrast slide. The essence of parallel is there are no dependencies. I'm just blasting hardware. If you got no dependencies, you just go, go, go. Nobody's waiting on anything. That's parallel. Concurrent means you got dependencies and they're interacting, and you're going to resolve this one before you can go to that one. You have memory fences, atomics. There are a lot of ways to resolve interacting dependencies, but concurrency is about managing complexity, usually because your algorithm, your system, we want that complexity. We want these handoffs to occur. So parallel when you can, concurrent when you must. Well-defined behavior. This is a good slide, and this is kind of the summary. Well-defined behavior comes from logical sequence. That's true. Defined by logical dependencies. That's true. Undefined behavior comes from physical sequence. No dependencies exist, therefore order cannot be controlled. The correction for undefined behavior is always to add a logical dependency, and then you get well-defined behavior. So if you're in the land of undefined behavior, you add a dependency, now you're well-defined. So we live in the land of well-defined. Don't ever live in the land of undefined. We do through assumptions of execution or whatever, but if it's important, put a dependency on it. That's it. And Rodney Dangerfield, he died a few years back, but he's that comedian, I don't get no respect. He's Groucho Marx, Henny Youngman, that era. So there he is. So that's kind of it. So think in logical dependencies. You'll stay in the land of well-defined. Assume everything moves all the time, and it will. It will for everybody. It's just that some of the higher order languages, they slap so many dependencies on it to get sequential execution to occur in that halted fashion. You're really going to pay a penalty for that. We're opening up the door for the CPU and the compiler to actually leverage the hardware we're given. So that's why stuff moves all the time. And that's good. We want that. So you can go into the other phenomenon to kind of reason about corner case failure, but the goal really being define your algorithm based on what you know, which is logical dependencies, and the push for functional programming is because some of these things are so well defined, mathematical expressions, you don't have an assignment operator, it gets easier. That's really the goal there. So any thoughts? I think we're kind of close. Anybody have any questions? What do we have? 6 minutes.
So, very interesting talk, thanks. You have kind of an implicit understanding of, or you left it out intentionally, granularity on this reordering type stuff. And there's obviously a continuum here all the way from instructions themselves all the way up to entire functions and maybe even entire programs on a supercomputing scale. And what changes there is obviously the amount of time you have to make the decisions of how to reorder things. But it's definitely a continuum. My question is, where should these sorts of reorderings be addressed? At the CPU level, at the program level, at the software level, at the library level, and particularly with respect to that continuum problem?
Yeah, so I completely agree that it's a continuum problem. And because it's a continuum problem, you have to address it at the continuum levels. So for example, the chip vendors, they have to resolve the dependencies. That's their job. The compiler vendors, they actually have to ensure the instruction stream is laid out in a way that stuff does get resolved and optimized. And then in your code, we do atomic level reasoning, like for a lock-free algorithm, that would maybe be in a function and locally. But as you go up, as you get into higher levels of buffers and containers and cache management, and then higher up, like into network and distributed and LAN, it's actually the same exact problem. I asked for this, I don't have it, I gotta wait. I don't wanna wait, so I'm gonna do something else until that value comes back. So the techniques are similar, they're expressed differently, but the answer to your question is, it's going to be addressed at all the levels. The library vendor will have to address it just as the compiler vendor does, and the application author, you'll have to resolve it too. You're going to structure, I have a task queue, so I'm doing other tasks while that thing comes back. Or, if you have threads or yields, or you can have more concurrency or less concurrency, that's going to be the architect. So at the higher level, it's a strategy. Is really the goal.
You use the word dependencies a lot, and you mentioned once that a statement is sort of an implication of a dependency. What would you say are like common control structures that people write in their source code where they think they might be dependencies, but they actually are not?
The biggest one I've seen is the order in which arguments are passed to a function that's unspecified, right? That could happen in any order. Don't use... Yeah, there is a proposal about that. The order in which globals and statics are initialized is not specified, so people will bite themselves on that. And we have a lot of techniques to get around it, but they're not aware that this global is being used. Yeah, so globals, order of function, well, the function arg thing is going away, but globals is a big one, and mutating a value within an expression where that value also is used. Don't do that. Yeah, other thoughts?
You said mutating a value within an expression is used. What if I say vector of I++ equals something else, right? So I'm technically using the value of I and also mutating it in the same expression. So how exactly does that work? Because it seems to work.
Yeah, so in the case of like a higher order type, like a vector, the documentation will say what's well-defined. So you're getting a value or a reference or what's allowed to express. The easiest one to say that's bad is f of I, comma, I++, comma, I++. I guess that will soon be well-defined. But f of I, comma, I is assigned the value of a, well, expressions, primitive types or higher order types, they're going to have to tell you what is controlled. An atomic value, a primitive value, can only control, I have this state, people are modifying my state. That's all their context. So they can't give you any guarantees past that. So anything higher than that, two threads want to bang on the same data object. That poor little data object, unless he's a higher order type with some thread safe interface, it's the job of the user to reconcile that. So you can have types that modify multiple times, chain, object dot, object dot, object dot. That's a pattern, right? We do that a lot. So that's a case where it does mutate through, but that sequence is well-defined. So as long as you're sitting on well-defined, you're good. And then somebody doing a code reveal will say, you're using something, you're making an assumption. That's going to be the problem, the loss assumption, if it's not well-defined. So. Okay, so I think that's it. There's do have a look at single static assignment and some of the compiler CPU internals. The cache line is actually a very interesting design element that will be increasingly relevant in our multi-core world. So we'll do that other talk some other time. Thanks.